We also discussed a concept called dimension of a physical quantity and also the dimensional symbol, right? And we discussed that mass have a dimensional symbol capital M, length have a dimensional symbol capital L, time has capital T, and also force has capital F, right? These dimensional symbols are different than unit symbols, and they are actually describing what that quantity actually is, right? So there is a principle of dimensional homogeneity which states that all physical expressions, relationships which we develop to explain a real phenomena, those relationships, mathematical relationships, should be dimensionally homogeneous, right? So whatever quantity you have on the left-hand side should have the same dimensions as the dimensions of the quantity on the right-hand side of that equation, right? So I will explain it using an example. Let's say that I give you a problem where there is a ball lying on the surface having a mass m, and it is applied with a force F resulted in the motion of that object, and the ball finally reached to this new point, actually covering a distance equal to, let's say, small x, right? So because of the application of force, there was a movement. Ball had some velocity. Let's define it as v. So v is the velocity. And it covered a distance of x in length, right? And in order to describe this physical motion and this phenomena, let me give you an equation. F times x is equal to 1/2 mass times velocity square. Now, this is an equation. Some of you might guess already that what I did actually, I equated the work done by that mass with the kinetic energy of that. But let's not discuss about the equation itself. Let's say that you were given this equation, you actually derived that equation describing this physical motion, right? Now, in order for this equation to be correct, it must be dimensionally homogeneous. Whatever are the dimensions of the quantities on x on left hand side should have the same dimensions as right hand side, right? So, for example, let's work out the dimensions of this equation and see whether it is dimensionally homogeneous or not. Force obviously will have a dimensional symbol F. So let me just write F. Generally, these dimensional symbols are written in square brackets, right? But please note that these are symbols written in square brackets. They are not matrices, right? X will have the dimension of length, right? It is a length which that mass traveled. So it should be having a dimensional symbol capital L. So F times L is equal to 1/2 is a dimensionless factor, right? It's a constant dimensionless factor. It doesn't have any dimensions. M is a mass of that object, so it should have the dimensional symbol capital M. And v is the velocity, which has a units of meter per second or feet per second. And the dimensions will be actually length divided by time, right? Meter per second, feet per second. So length divided by time. So it should be L divided by T. So let me write it as LT raised to power -1. And there is a whole scale of that velocity scale. So therefore, there should be a power 2 here, right? So I write the same equation, but now instead of using its notation, I am using the dimensional symbols, right? Now we know that in SI system, force is a derived quantity which can be written in terms of mass, length, and time, right? So we know that F is equal to ma. So which means the dimensions of force is equal to the dimensions of mass times the dimensions of acceleration. So the dimensions of mass is m multiplied by dimensions of acceleration is length divided by time square, meter per second square, feet per second square, right? So length divided by time square. So let me call it LT raised to power -2, right? So the dimensions of force can be written in terms of dimensions of mass, length, and time. So it is mLt raised to power minus 2. So let's replace that here. So now the left hand side will become m multiplied by L t raised to power minus 2 multiplied by L again is equal to m on the right hand side. And then you will have L raised to power 2 multiplied by t raised to power minus 2, right? So that scale will go to both. And you can see that this equation is now dimensionally homogeneous. Since these are simples being multiplied, they are not matrices, so their order doesn't matter. So you can see the final quantity which you have on the left hand side, ml raised to power 2, because it will be multiplied by this, multiplied by t raised to power minus 2, becomes same as what you have on the right hand side. So this equation is dimensionally homogeneous, but again I would say that this is not the only condition to check. It is not a sufficient condition for an equation to be correct. It is one of the many conditions which that equation should satisfy, right? So whenever you derive an equation, you can apply that check as a first check whether that equation is correct or not. If, for example, you are doing some calculation and you are supposed to determine a force, and all the units are not kind of cancelling and finally giving you a force units at the end, it means you have some mistake in that particular problem. So this is a very useful tool to check the correctness of equations and calculations. But obviously, this is not a sufficient condition. A wrong equation can also be dimensionally homogeneous, right? A wrong mathematical equation can also pass that check.